Hi, welcome to the demonstration about lab activity A to B. It says consider the given circuit above whose analysis and simulation were done before, and construct the following the above circuit on your breadboard using a 9-volt battery as a voltage source. We have seen this circuit in our lecture. It was here. This is the same circuit, but there is an extra current source. Well, at the end of calculations, we assumed it is 0 amp, so the circuit will be the same. We have made the calculations, and the result was E1 is 4.15 volts, E2 is 4.85 volts, and we have calculated some other values, for example I1, the current on R1, and the power dissipated by resistor 1. I4 is 1060 microamps. I0 is minus 1.66 milliamps, and we have easily calculated the other values after calculating the node voltages of the circuit. And in lab activity A to A, we have made the simulation of the circuit. This is the simulation values. Now it's working. The simulation program Multisim is working now. As you see, it shows the same values. The voltage of this point is 9. The current through voltage source is minus 1.66 milliamps. And the voltage of E1, node E1, is 4.15 volts. Voltage of E2 is 4.85 volts. And we can easily find the other. We can easily calculate the other values of the circuit. Yes. Let's return to our physical circuit. Here I have a breadboard, and there is a 9-volt battery. 9-volt battery. It has a socket. There are two cables. One of them is red, as you see, and the other is black. Black is connected to the negative terminal of this battery, and red is connected to the positive terminal of this battery. And as you see, black is directly connected to this line, so it's all 0 volts, and red is connected with a gap. There is a gap here, discontinuity, and then it's connected to here. The upper line has 9 volts if I connect these two cables. I have made a discontinuity here because I will put a power switch. I will insert it, so whenever I wanna make it off, I can adjust this switch, so I can turn the circuit off easily. Now it's in off state. Let's look at our circuit. There is a 9-volt battery as a source, and this point is 9 volts. There is a 8.2 kilo ohm resistor connected to the 9 volts, and let me connect it. As you see, this is an 8.2 kilo ohm resistor. It has the colors gray, red, red, 822. I'm inserting this on the breadboard. This point is 9 volts, and this point is E1. The other terminal of the resistor is E1. And then let's look at the circuit again. R2 is 3.9. R2 is 3.9. So it should have the values orange, white, and red. I have one resistor, 3.9, and one point of 3.9 should be connected to the ground. This line is ground, and I have connected it to the ground. Now these 2 points should be connected, so I need a cable, conductor cable. I have a cable like this. I'm inserting it to make a connection. And now I need a 3.9 resistor again here. Yes, it's a 3.9 kilo ohm resistor, but let me insert it first. I need a 1.5 kilo ohm. Let me insert it first. This is 1.5 resistor, kilo ohm resistor. It's brown, green and red. I'm inserting it here, and I put a connector cable, conductor. Then here I will put a 3.9 kilo ohm resistor. This is E2, node E2. One terminal of this resistor is connected to the 9 volt and the other is connected to E2, node E2. And here I have to connect a 8.2 kilo ohm resistor as it's expressed in manual. I'm connecting it, and there is no connection, as you see, between these two, so I need another cable wire. Now I have connected these two these three resistors. So this point is E1, this point is E2, here is ground, here is 9 volt. Then I can power my circuits. Now I predict that it's working. Let's turn to the manual. It says look at the voltages of loops and currents through nodes. We can look at using multi-sim simulation of the circuits, and you can measure all voltages and currents using your multimeter. Okay, let's measure the voltages and currents of our circuits. This is my multimeter, and looking at the circuits, V0 is defined in this polarity. This is minus sign, this is positive, plus sign. V1, for V1 this is plus, this is minus, and for V2 this is plus, this is minus. If you write the KVL equation for the first loop, we have to write minus V0 plus V1 plus V2 is equal to 0. This is the KVL equation for the first loop. So I will measure these values and see that KVL holds. This is the multimeter. It's measured. I have adjusted it for DC voltage. Here it's in DC voltage measurement mode, and the probes are connected like this. Black is connected to the common, and the red one is connected to the voltage mode. Now let's measure. I know that this point is ground, so it's accepted as the reference, and this point is connected to the voltage source. I expect this point to see 9 volts. Yes, as you see, it's approximately 9 volts. It actually reads 9.37 volts. And this is E1. I expect to read, yes, this is the voltage of V0, voltage across V0, or I can read like this. V0. So I will write minus 9.37, and then I will measure V1. Yes, this is the V1. Please consider the polarities. I touch the red one to the upper side because it is defined as the positive terminal of V1. It reads 5.05 minus V0 plus V1 plus V2. V2 is defined in this manner. Upper side, this side is positive, this side is negative. I read 4.32. And as you see, it's approximately 0. So KVL holds. Now I will show that, yes, look, minus V1 plus V1 minus V0 plus V1 plus V2 summation with 0. So KVL holds. Let's see whether KCL holds. This is our circuit. For example, I will apply the KCL equation, KCL method on these nodes, and I will add this current, and this current. So I4, I3, the summation of I4 and I3 will be equal to the I5, excuse me. I3 and I4 are entering, I5 is removing from the node. So I have to write I3 plus I4 is equal to I5. This is KVL, this is KCL. So I have a voltage in terms of volts, and I have resistors in terms of kilo. So I expect to have some current in terms of milliamps. So I adjust my multimeter in milliamp modes. And as I said before, this is the black side is connected to the common, but for measuring some current I have to change my red probe. It should be inserted here because I expect to measure some current in terms of milliamps. Okay. And in order to measure some current, I have to open the circuit. For example, I will measure the current flowing on R4. So the I4 is defined flowing from up to down in this manner. This is positive, this is negative. So I will measure the current of this coil like this. Current is coming like this. So I have to touch the red side here and black side here. And what you see is 1.1 milliamp. I3 is 1.1 milliamp. Do we expect it? Let's look at the simulation values. Okay, it's expected. It's very closer to this value. This is I4. So I made a small mistake here. This should be I4. I4 is 1.1. Let's look at what's I3. I'm completing the circuit and I'm opening this port. Because I3 is defined in this direction from here to here, I have to measure it like this. It should be coming like this. It's entering into the red color, red probe, and going out from the black one. and what I see is minus 1/2. Yes, minus 0.49. Let me write minus 0.49 plus I4 should be equal to I5. Let's measure I5. To measure I5, it's going in this direction. I am opening the circuit and I'm touching the red one here because the defined current is coming here and going on the black one, and what I read is 0.78 or 77. So as you see, they're approximately equal. Yes, so KCL holds. Okay.